Hello everyone, welcome to my talk. I first want to thank the organizer for giving me such a good chance to introduce our recent work, in which we generalize a Renai theorem for spectrally positive stable processes. Okay, we start our talk by introduction Renai theorem for Brownian motion. We denote B as a standard Brownian motion. Okay, and LB xt be the Brownian local time processes. Okay, and we define a stopping time tau BL zeta, and here zeta is a positive constant. It means the first time that the amount of local time accumulated at level 0 exceeds zeta. Okay, it's defined as following. The standard Renai theorem tells us that the Brownian local time process LBT tau BL zeta, okay, it is a zero-dimensional Basel processes, okay? It is also a critical Feller branching diffusion, and it solves this SDE, okay? With WB as a standard Gaussian white noise, okay? It is obvious that Y zeta, actually it is a continuous martingale, and also it is a strong Markov processes, okay? Let us go to stable processes, okay? And we denote Xi as a one-dimensional spectrally positive stable processes. It is uniformly determined by its Laplace exponent phi lambda. It is equal to B lambda plus C lambda 1 plus alpha, okay? And B is a non-negative constant. C is a positive constant. And alpha is constant in the interval 0 to 1, okay? So Xi is an alpha stable processes, all right? And also it is also the Laplace exponent also can be written into this form, with the mu alpha as is known as a Levy measure. Okay, it is a sigma finite measure on the positive half real line. Okay, we define W as the scale function of Xi. Okay, it is equal to 0 on the negative half real line. Okay, on the positive half real line, it is uniformly determined by the Laplace transform this, okay? Okay, and W actually is a smooth function on the positive half real line, okay? We denote W prime as its derivative, okay? Now we continue to consider its local time processes L Xi xt. Okay, actually it is jointly continuous, all right? But Xi is not continuous. From Theorem 1.1 in Eisenbaum and Caspi, 1998, we see that 1993, we see that the local time processes L-Xi actually is not Markov. And also, L-Xi is not a semi-martingale. Okay, all right. We still define the stopping time tau Xi L zeta as before. All right, okay. Now we know that for any positive zeta condition on the stopping time tau Xi L be finite, we will see that the local time L Xi T tau zeta L tau Xi L zeta actually is the unique weak solution to this stochastic vector equation. Okay, with N alpha be a completed Poisson random measure with intensity ds v alpha dy dz. Okay, you will see that the coefficient b comes from the stable processes. Okay, and also v alpha is the Levy measure of Xi. Okay, and this is the scale function. You will see that every jump in the stable processes with size y will make its contribution to the local time follow in this way, okay? And as we know that W actually is a continuous function, we will see that this integral actually is continuous, okay? And then we know that X zeta is continuous. Based on this equation and the Kolmogorov continuity theorem, we will see that X zeta actually is a local Hodel continuous of any order less than alpha over 2. And this result had already been proved by Ballot in 1988. Okay. Another thing is for any t be positive and any theta less than alpha over 2, we will see that the Holder coefficient defined as this, okay, it is standard definition. We will see that this random variable actually have finite moment over all orders, okay. This result had already been proved by Foreman in 2008. Okay, now we go on to consider the distribution over these processes, okay, by studying its characteristic functionals, okay. Now we introduce several notations. We first define a function kt as this, okay, and we define an operator v alpha. It acts on an c-valued function f in this way, all right. And actually, you will see that this is very similar to the Laplace exponent of a Kc formula, okay, in form. Okay, we define C minus as a space of all complex numbers with a non-positive real part, okay, and B as a space of all bounded C minus valued functions on R plus, and F star G is the convolution of two functions F and G. Okay, it's defined as this, all right? Okay, we will say that for any lambda in C minus and G in B, okay, we will say that the characteristic function of x zeta has equal to the exponential function to the power alpha zeta times k star v lambda g t, okay, all right. And this function v lambda gt actually is the unique global function to the nonlinear Valtteri equation, okay, this equation. Since as we know that w prime is singular at 0, we will say that v lambda g will go to infinity as t go to 0. That means v lambda g is a singular at 0. All right. Anyway, but up now we have introduced the stochastic Valtteri equation and also this nonlinear Valtteri equation. These two equations are too complicated for us to make out the structure of the local time processes. So we introduce another equivalent representation for them. Okay, we denote R rho A and D rho A to be the Riemann-Rouville fractional integral and derivative operator of all the rho. Okay, it is modified by a constant A, positive constant A. Okay, it is defined as this, and when A equal to 1, it will reduce to the standard Riemann-Rouville fractional integral or derivative operator. All right, we will see that the stochastic Valtteri equation 1 is equivalent to this fractional stochastic equation, okay, integral equation, okay. All right, you will see that any jump with size y will make its contribution to the local time processes in this way, all right. And also, the nonlinear Valtteri equation 5 actually equivalent to the following fractional Riccardi equation, all right. Okay. Because of the limitation of time, we have no enough time to introduce the proof. At the end of this talk, we give our conjecture for the Riemann theorem for general spectrally positive Levy processes, okay, with Laplace exponent in this form. B is the drift, okay, it is the non-negative. Sigma is the diffusion, and this one is the jump, okay. The Levy method satisfies this condition. That means Kc has finite first moment, okay? All right, and its scale function W is absolute continuous on the half real line, okay? And its random nickname derivative is denoted as W prime, okay? And its local time process LKC is joint continuous almost surely if only if this integral is finite. Right? under this condition, we will say that the local time processes LKC actually is the unique weak solution to this stochastic Velter equation. Okay, this one comes from the drift. Okay, this term comes from the diffusion, and this term comes from the jump. All right. Okay, here WKC is a Gaussian white noise with intensity ds dz. Okay, NKC is a composited Poisson random matter with intensity ds mu dy dz. All right, and this term tells us the jump with size y, how the jump with size y contribute to the local time processes. Okay. All right, that's all the things we want to introduce. Thank you.